In this video, you'll learn how to apply the F-test to determine whether variances are equal for two samples. The data shown here are monthly units of cars sold for two large car dealerships in the same town. Average sales are about the same, but the owner of Sharkey believes his sales are more consistent, that is, have less dispersion around the mean. We will determine at the 0.01 or the 1% level of significance whether the owner of Sharkey is correct. Our alternative hypothesis is that the variance for Dave White is greater than the variance for Sharkey. The null hypothesis, therefore, is that Dave White's variance is smaller than or equal to Sharkey's. There are two ways to run an F-test in Excel. I'll demonstrate both. Because we need to run the F-test with the largest variance in our first sample, we need to use the var.s formula to check. Here we'll type equals var.s and then select the sample of Sharkey's sales, and we will do the same in the column for Dave White. And as you can see, Dave White's variance is larger than Sharkey's. Our F-test will determine if it is significantly larger. Now we can go to Data, Data Analysis, and select the F-test to sample for variances. Our variable 1 range again will be the sample that had the larger variance. Variable 2 will be the smaller variance. I included labels, so we'll check off labels, and we want to run the test at the 0.01 level of significance. I'll have my output range here, and here is the output for the F-test. This F-test specifically provides output for a one-tail test. We can either compare F to the F-critical one-tail, where we will reject the null hypothesis if our F is greater than F-critical, or we can look at the p-value. If the p-value is smaller than alpha, we reject the null. In this case, our p-value is 0.15, which is larger than our alpha of 0.01, and our F is smaller than F-critical. In both cases, we fail to reject the null hypothesis. There is insufficient evidence to conclude that Dave White has higher variance than Sharkey. Note that this conclusion is reached even though the actual variance is larger. That difference is within the allowable limits given our small sample size and thus the small number of degrees of freedom, which results in a large F-critical value. The second method of solving will only solve for the p-value, and it returns the result of a two-tailed test using Excel's f.test function. I'll demonstrate below the table. Equals f.test. My first array is again the one with the largest variance. Sharkey's sales will go into the second array. Close parenthesis and hit enter. And it returns a p-value for a two-tailed test. Of course, we're using a one-tailed test here. And so we can divide that p-value in half to get the one-tailed portion of it. And as you can see, it matches exactly with the p-value we saw in our F-test two-sample for variances. This video demonstrated how to use Excel's F-test two-sample for variance and the f.test function to compare variances for two samples. In this video, I'll demonstrate how to use Excel's data analysis tool, Anova single factor, to run a one-way Anova and test the assumed equality of more than two population means. A real estate developer is evaluating 3 parcels of land for a retail development. Of importance in the final decision are the mean incomes of nearby households. A random sample of 4 households' income in the area has been collected. At the 0.05 significance level, can the developer conclude there is a difference in the mean income between potential locations? Our null hypothesis is that all means are equal. The alternative is that they are not. Go to Data, Data Analysis, and find Anova Single Factor and click OK. Our input range will be all of the data from Southwick through Old Orchard. Our data are grouped by columns, that is, each sample is in a column rather than a row. Labels are in the first row. We will leave it at an alpha of 0.05 and put our output here in our worksheet. Now I'm ready to click OK. And here is my output. At the top we see some descriptive statistics on our data set, the average and variance, and our sample size for each of the 3 samples. In the analysis of variance table, between groups is Excel's term for treatments, in other words, the sample which represents each population. Within groups is Excel's term for error. The value in SS next to between groups corresponds to the sum of the squares due to the treatments, or SST, and the value in this cell is SSE, the sum of the squared errors. MS is mean square, and MS in the between groups row is therefore MST, mean square for treatments, while in the within groups row it is MSE, mean square error. We can either evaluate the critical value against the test statistic or use the p-value. Starting with the calculated test statistic, the F of 14.179 is much larger than the F critical value. We would reject the null hypothesis and conclude that the means are not equal. The p-value leads to the same result. It is the probability of getting the calculated F statistic if there really were no difference between the means, and 0.0017 is much smaller than our alpha of 0.05. Again, we would reject the null. Note that we cannot conclude which of the means may be unequal, only that the 3 means do not equal one another. If we want to go a step further and determine which pairs of means are unequal, that would require additional testing. This video demonstrated how to use Excel's Anova Single Factor tool to conduct a one-way analysis of variance on sample means to determine whether the population means are equal or unequal. This video will demonstrate how to apply Excel's Anova Two-Factor with Replication to evaluate interaction effects of 2 variables on a response variable. In this file, we have a sample of weekly wages for 5 male and 5 female accountants in the public sector, and for 5 male and 5 female accountants in the private sector. Our main hypothesis is that there is no interaction effect between gender and sector affecting wages. The alternative hypothesis is that there is an interaction. We will also test whether there is a mean difference in wage by gender and in wage by sector. We'll test at the 0.05 significance level. We need to put the data into an appropriate format before we can run the test. The Anova dialog box expects us to state the number of rows in a sample. We will be able to tell Excel that we have 5 rows per sample. Now that we've grouped the data, I'll go to Data, Data Analysis, and select Two-Factor with Replication. In the dialog box, the input range will go from gender to private and down to the last value. Our rows per sample are 5. Our alpha we will leave at the 0.05 level. Let's put our output range in this spreadsheet and click OK. In the top of our output, we have summary statistics for men and women, public and private. As you can see on column L, we have the total sum and average and variance for all of the males in the sample, sum, average, and variance for all females. Within the table, we have the average and variance of the 5 males' wages who are in the public sector and 5 in the private, the same for women. And at the bottom we have the total of the public and the total of the private columns. Now let's look at our Anova output. The first row, the sample, corresponds to mean wages for men versus women. The columns row compares mean wages by sector, and the interaction row, of course, indicates if we have a significant interaction between gender and sector. The within row is our error row. The p-value for gender is 0.004, less than our 0.05 alpha. Of course, we can also look at the F versus F critical. 11.44 is greater than our F critical of 4.49. In either case, we would reject the null and state that there is a difference in mean wage between men and women accountants. For sector results, that is the columns, let's change the p-value from a scientific notation to a number. Again, we would reject the null and conclude there is a difference in mean wage between private and public sector. For interaction, however, our p-value is 0.067, greater than our alpha. The F is smaller than our F critical. We cannot reject the null for interaction. We conclude there is no interaction effect between gender and sector on wage. This video demonstrated how to conduct a two-way analysis of variance to test for an interaction effect of two variables on a response variable by using Excel's Anova Two-Factor Anova without replication. This video will demonstrate how to conduct a two-way analysis of variance. We will study the separate or independent effects of two variables, also called factors, on a response variable by applying Excel's Anova Two-Factor without replication tool. In this dataset, a company runs production for 3 shifts, 5 days a week. Employees rotate shifts, and management is interested in determining whether there is a difference in production output by employee depending on which shift is worked. A random sample of 5 workers is selected and their output recorded on each shift. At the 0.05 significance level, is there a difference in the mean production rate by shift or by employee? The rows correspond to our blocking variable, the 5 employees. The columns correspond to our treatment variable, the mean output per shift. We have 2 sets of hypotheses. The test of hypothesis for our treatment variable is that production means are the same regardless of time of day. Therefore, the null hypothesis is mu1 equals mu2 equals mu3. The alternative hypothesis is they are not equal. For the hypothesis of equal block means, we will use employees' initials to tell them apart in our notation. Mu s equals mu l equals mu c equals mu t equals mu m, where the s stands for scuff, the l for lum, and so on. The alternative hypothesis is that the means are not equal. Go to Data, Data Analysis, and select Anova Two-Factor without replication. In the input range, select from Employee through Evening and down through Morgan's output. I've included labels, so I click Label. Leave the alpha at 0.05. Output can stay in this tab. Let's have it here in cell F1 and click OK. Here is my output. We have descriptive statistics at the top for each variable. A summary of the blocking variable is first, then the treatment, and that corresponds to the order in the Anova table. We can compare F with the F critical value or look at p-value for our rows and our columns. For the test of employee production equality, which is our rows or blocking variable, F of 1.55 is smaller than F critical, and the p-value is larger than alpha. With either outcome, we fail to reject the null hypothesis. We cannot conclude that there is a difference in output by employee. For the treatment, that is for the columns row, f of 5.75 is larger than f critical of 4.46, and our p-value is smaller than our alpha. We reject the null hypothesis and conclude that there is a difference in mean output per shift. Note that we are not able to conclude which shift is different from another. We can only conclude that there is a difference. Further testing would be needed to determine where the difference lies. This video demonstrated how to conduct a two-way ANOVA of two independent factors on a response variable using Excel's tool Anova Two-Factor without replication.